There we go, I think. Okay, so this is the periodic table. I was hoping that by now that they would have the bigger one up in here, but they don't yet. Hopefully they will soon. But until then, we can go ahead and just use, and if they don't by the time that we get to the actual exam, then I'll make sure that for the exam that you're given the periodic table. I do want you to know, and I expect you to memorize the element names and the order and their symbols up through calcium. Because it's pretty easy to do that, to know them in order. You're going to see them over and over and over again, and it'll just help out a lot. There are others that you're probably going to memorize or know just starting seeing them over and over and over again, or the common ions, which I did notice in your book, but I also put them on the PowerPoints and on the videos. So, ones that are common that you're going to just have to, at this point in time, unfortunately, you just have to memorize them. But just to review so far, the portion, let me just, alright, should let me write on this, yep. Okay. With the exception of hydrogen, so hydrogen and all of these on this side of the periodic table, are those metals, nonmetals, or metalloids? Those are nonmetals. Okay? Everything, now let me, then if we just imagine a stair step, starting here at this corner of the periodic table, and you work your way down, okay, so up, that's going to tell you the metalloids. Everything that borders on two sides except for aluminum. So aluminum doesn't count. And what was the other one that didn't count? Polonium. Except for those two, because those two are not. But everything else that borders on two, so we're talking about boron, silicon, germanium, arsenic, and so on and so forth. Those are called metalloids. And in a future chapter, we'll talk a little bit about the characteristics of metals and metalloids and nonmetals. Everything else, including aluminum and polonium, are metals. Okay, so the majority of these are called metals. Now, in the metals, we do have the transition metals, or sometimes they're also called the transition elements, that are in this little section. And I'll explain later, I think it's chapter 6, 7, or 8, that will talk about the reason why they're offset like that. And it'll make more sense right then, whenever that time comes. Okay? Those are called the transition metals. And then also as a review, not including hydrogen, but what are, from lithium down to francium, what are those called? Alkaline metals. And the group 2A, what are those called? Alkaline earth metals. And if we skip all the way over here to group 6A, sometimes it's also called group 16, but I don't like knowing those numbers. It's always too difficult for me, but the 6A, and that'll make more sense later on why I leave it as a 6. 6A, those were called chalcogens. 7A were the halogens, that's fluorine. And then we have, last but not least, the noble gases, sometimes called rare gases, sometimes called inert, but we'll just stick to calling them the noble gases. And then the last two that are special, which they're already given down here, are the lanthanoids, or sometimes called the lanthanides, and the actinoids and actinides. And the way that this is set up, it's kind of odd in that this little section here is where 57 through 70, so lanthanum through ytterbium actually is supposed to fit right there. That's like a little insert. And likewise, from actinium to nobelium is down in the section just below it, between iridium and lawrencium. Okay, so that's why, and it'll make sense by chapter 8, the reason why those are offset where they are. Because it has to do with the number of electrons that they have in their outermost shell. All right. So, this brings us up to the idea that we had isotopes. And isotopes, well, actually, before we do that, if we want to keep on reviewing, every element that, well, so for example, let's just take any of these. Take calcium, for example, where will all calcium atoms have the same number of electrons? Is it the electrons that gives calcium, that makes calcium calcium, so to speak? No. What subatomic particle is it that gives calcium calcium? Protons. And they can also vary in the number of neutrons. So if we stick with calcium, first of all, no, I've got it hidden. What's calcium's chemical symbol? Ca. Okay. And let's see, its number's 20. Let's say that we have one that's calcium 44, for example. All right. So just by, if I only gave you this right here, I would expect for you to be able to tell me the number of protons, the number of electrons, and the number of neutrons. Right? So, how many protons are there? There are 20. If we assume that this is a neutral atom, how many electrons are there? 20. How many neutrons are there? 24, because you take that mass number, which is the 24, and you subtract out the atomic number, which was a 20. Now, what happens if, let me erase these. I say this, and I'll change the color perhaps. What if it's calcium 2 plus? First of all, is it now, what is this now? Is this now the elemental calcium or is it a calcium ion? It's an ion. And what type of ion? Is it cation or anion? Cation. So now how many protons are there in this calcium? There's still 20. How many electrons are there? 18. That's the reason why there's the 2 plus charge. And then how many neutrons are there? 24. Because the number of neutrons doesn't change with respect to this. Okay, we're going to find out later on there is a way to change the number of neutrons. That's next semester with radiochemistry and nuclear chemistry, when we talk about different types of radioactivity. But you can't change the number of protons because otherwise it's no longer that element. It's going to be something else instead. All right. So let's go back up here. And we're going to start to review a little bit with respect on the naming and the different ions that you needed to know. There's those that are called monatomic ions, which just means that they have one atom, the ion. So for example, like calcium 2 plus is monatomic. And then you can have those that are polyatomic, which means there's more than one atom that's involved. And so one example for that would be something like nitrate, which is NO3, which what's the charge on nitrate? Has anyone already started memorizing these? It's -1. Which if it's a -1, a lot of times I'll put a circle around it so that way you can tell it's a minus or a plus versus just, it makes more sense that the circle does once we start doing chemical reactions, because whenever the equations, sometimes it's hard to tell if you're talking about a cation or if you're just using a regular plus sign. Alright, so that's the nitrate. But now let's start, and that's polyatomic. Most polyatomic ions are going to be anions. They're going to be negatively charged. The big exception, the one that's a polyatomic cation that's common, is ammonium. And what's the chemical symbols for ammonium? NH4, and the charge on it is +1. Okay? And once again, I want to reiterate the fact that whenever we talk about charges, if it's just a +1, you just have to put a plus, or a -1, you just put the minus. But if it's a +2 charge, you actually put the 2 first and then a positive sign. If there's a +3, then you put the 3 first and then the plus sign. Alright, some of the other common ones you need to know. Hydrogen, is H plus. Unless it's a hydride anion, then it becomes H minus. So it can actually go either way. Other common ones, sodium and potassium. And what are the charges whenever they become ionic? Positive 1, okay? Same thing with lithium. And you're going to find out by like in chapter 6, 7, and 8, that's actually the reason why I used to skip to chapter 6, 7, and 8. You're going to find out the reason why they're plus 1. But the elements that are in that first family, so the alkali metals, they like to be plus 1 whenever they become ionic. On the other hand, the elements on the right-hand side of the periodic table, they tend to lose electrons, and those that are halogens tend they tend to gain electrons. I'm sorry, not lose electrons. They tend to gain electrons, and they like to gain 1. And the reason why is they want to look like the noble gases, and so that's why fluorine becomes fluoride, because IDE means it's negatively charged. Chlorine becomes chloride when it gets a -1 charge. But we've already been doing that whenever we talk about sodium chloride, which is table salt. And so you've already been, that's how you actually know more about naming compounds than what you realize. At least for some of those more common ones like sodium chloride, potassium chloride, potassium bromide, and iodide. All right, so let's just do another one. Oh, I already did that one. Give everybody a moment to write this one down. And even though technically Fe is not in the first 20 elements, it's one that you're probably going to, if you don't already know it, you're probably going to know it soon. Okay. So let's name this one. Okay, and we're gonna sort of, just for those who haven't done a lot of this before, this right here is a polyatomic anion. You always name, and actually the way you write it out too, chemical formula wise, is you always put the positive first and followed by the negative. Okay, so that's the sulfate. And what's the charge on the sulfate? You're right, it's a 2- charge. Okay, and then Fe is iron. So with the cation, you just write out the word, so it's iron. Now, the reason why, so you have to be careful if it comes from a transition, one of the transition metals. Many of them, not all of them, but many of them actually can have more than one charge. Okay, and iron is one of these. So since I gave you the formula here, you can already tell what charge it was since it's in a 1-to-1 ratio. There's 1 iron to 1 sulfate. Since the charge is a 2- on the sulfate, the charge on the iron has to be 2+ since it's a 1-to-1 ratio. And so in parentheses, you put Roman numeral 2. So it's iron 2 sulfate. Okay. So then let's work this going backwards. So give everybody a moment to write it down into attentive. This is manganese 5 nitrite. Yes, usually the book will have one on the cover, if not elsewhere. So I think it's in either the front cover or the back cover. And likewise on a quiz or an exam from here on out, if we don't have it in the room or wherever you're taking the quiz or exam, then I will make sure that you have access to a periodic table. You don't have to bring your own. The only exception to that is if I'm giving you a quiz wherever I'm asking you, what's the symbol for nitrogen, that kind of thing. That one, then I wouldn't provide you with the periodic table, obviously, for that. But it doesn't happen very often. Okay, I'm going to actually start with this one backwards. What's nitrite? That's one you just have to memorize. What's the symbols for the polyatomic anion nitrite? NO2. Because the ITE is the ending that has the. So there are 3 endings that can be signify negatively charged ions. IDE, like chloride, bromide, iodide. ITE, like sulfite and nitrite, and then ATE, like nitrate, sulfate, phosphate. The ITE is the one that gets the lower number of the oxygens, whereas the ATE ending gets the higher number of oxygens. So that's why nitrite is NO2 and nitrate is NO3. Sulfate is SO4 and sulfite is SO3. And then what's the charge on nitrite? It's -1. The manganese, which is not one that you'd have to memorize, I'd either give it to you or you'd look it up on the periodic table, and its symbol is Mn. And then, what's the charge on this manganese? It's a 5+. Because it too is from the transition elements, transition metal. Okay. So now we've got to put this together to balance out this ionic compound. So what will be the final formula for this manganese 5 nitrite? It's going to be Mn. There's only one of them because if you remember, it's actually fairly simple to do ionic interactions because the charge of this one becomes the subscript there, the charge of this one becomes the subscript here. So it's going to be Mn, and then how do we do the nitrite since there's going to be more than one? Parentheses. It's just like in in calculus too, but in algebra. So it's NO2 in parentheses 5. Now, later on, you're going to have to figure up, like when you haven't learned how to do it yet, but we're going to figure out how to do the molecular or formula masses for compounds. How many total number of oxygens are there in manganese 5 nitrite? 10, because you multiply everything out. So that there really is 1 manganese, 5 nitrogens, and 10 oxygens in that ionic compound. Right. So I've been alluding to this all along here, but there's so far you know of 2 types of intermolecular bonding. Okay, or I should say interatomic bonding. One is the ionic bond, which is formed between ions. And the second one are covalent bonds. And so if we look at the periodic table, so let me just do that briefly. We're looking here at the periodic table. What part of the periodic table is going to be, will make up an ionic bond? So it's metals. It's going to be a metal with a non-metal. Okay? And the reason why is you can just think of it like opposites attracting. Okay? So that's the reason why, for example, if we say sodium oxide, which we can actually do that now if we go back. Oh wait, that's not what I was wanting to do. Okay, so for the ionic, once again, we have the ionic. We have the example of sodium oxide, which is just an oxygen. And what's the charge on oxide, anion? And of course it's going to die right here in the middle. Alright, so it will become Na2O. The second kind of bonding, I don't know how long it's going to take for the projector to come back on, is called covalent bonding. Now, I'm not for sure if in this chapter they really use that term a lot. Some books don't. I don't know why they don't like to use that term at this point. And once again, we're talking about interatomic interactions, all within the same molecule. It's supposed to be turning itself on. But covalent bonds are usually going to be made up of atoms from what part of the periodic table? What kind of atoms make up a covalent bond? They're both going to be nonmetals, typically. So we're talking about nonmetals, between nonmetals. Okay. So here are just some examples. Of course, these two are the two that usually get used the most, okay, as the like quote-unquote textbook examples of it. Why is it not? Okay. Alright, it's supposed to be turning stuff back on. Alright, so if we're going to name these, we're going to name these covalent interactions and the covalent bonds for these molecules. Once again, you're going to put the one that is furthest to the left of the periodic table first, because it's called being less electronegative. But the book kind of says that, but they don't explain what that is later on. And usually we're talking about things like oxygen or one of the halogens will be the whatever is on the right-hand side. You always name this one first, so that's this carbon. And if there's only one of them, you don't have to say mono. Like we wouldn't say mono, carbon, whatever. However, for the second atom, you do. So this becomes oxide still, but it's going to be dioxide. Of course, you probably already knew CO2 is carbon dioxide, whereas CO is carbon monoxide. And once again, I mean, I won't take off usually for spelling, but since this ends in a vowel and this starts with a vowel, they usually just merge it together and say monoxide. All right. Or if we could have something like you'll find out that oxygen, sulfur, fluorine, bromine, chlorine, a lot of these are the ones that are involved in this kind of interactions. So we have P2O10, and we want to name it. Okay, P is the symbol for phosphorus. Okay, we already know the ending for this one's going to be oxide. But what's the prefix for 10? Deca. And it's fine with me if you either said deca oxide or if you just took the A off. I won't. I've seen it both ways. The deca oxide. And then we have the phosphorus. So I'm writing this out backwards. Phosphorus, which I cannot write. That's supposed to be phosphorus. And then now there's more than one for that first element. So therefore we have to include the prefix. And the prefix for 2 when naming, in this kind of naming, would be di. So this is diphosphorus decoxide. Okay. So you need to memorize the prefixes to 10. Okay. So there's, for this kind of prefix, there's mono, di, tri. 4 is what? tetra, not tetris. Okay, tetra. And then 5 is penta, 6 is hexa, 7 is hepta, octa, nona or nana for 9, and then deca for 10. Okay. I don't make you learn like 11 and 12, like undeca and dodeca and things like that. You're going to find out that there are others as well. Whenever we start doing the alkanes, then it's meth, eth, prop, ut, things like that. They don't use the same prefixes for the numbering system. Okay. Are there any questions so far? Anything like that? Because that's essentially chapter 2 in a nutshell. There's not a lot, and yet at the same time there really is. And I do give a lot of suggested problems. I'm working on suggested problems for the end of the chapter for chapter 3. But chapter 3 is very, very important. All right. So let me escape out of this. Why does it keep doing that? Was the law of conservation of mass. So it means that in a chemical reaction, the law of conservation of mass says that you have to start off with a certain amount of matter, you're going to have to end up with the same amount of matter. You cannot create matter and you can't destroy matter. It's just transformed from one form into another. So for example, if there were 2 carbons that you start off with, you're going to have 2 carbons in the end. They may have just swapped partners, but you can't, create or destroy matter, so to speak. Now we're going to find out that there's a caveat to that. It's called law of conservation of mass and energy, because there are ways that you can give it off in the form of energy in that sense. But we'll get to that later on in the semester. Yes?
Is this PowerPoint on my part?
No, not yet. Nope. All right. So chemical equations are just ways of representing the chemical reaction. Okay, this is using the space-filling diagram, which is not very useful. Okay, it shows you the relative size of everything, the types of atoms, but this is methane gas going into combustion kind of reaction. And so here what it is this is CH4 plus. So that's the reason why I always circle my charges, because that way you don't know, is that really a CH4 a cation or not? Well, you know it's not because of the fact that I don't have a circle around it. Plus 2 of the O2s. Remember, there are 7 naturally occurring diatomic molecules. Oxygen and hydrogen are 2 common ones. And then we have the halogens and nitrogen. And they're forming carbon dioxide plus 2 waters. So if we notice, we started off with 4 oxygens on the right-hand side. We have to end up with 4 oxygens, those little red balls, on the left-hand side. It's just that they are left-hand and right-hand. It's just the fact that they swap partners. Okay, and then the reaction arrow is showing you the reactants are on the left-hand side and the products are on the right-hand side. We're going to find out that that's not always true. There's something called equilibrium where they can go back and forth, back and forth, back and forth. But in this one, it's irreversible. It only goes one direction. It is not reversible. Okay. And then we can just skip right on through this. All right. So many times, not always, but many times, they also include the state of matter, whether it's a gas, a liquid, or an aqueous solution, or a solid. Okay, and so the 4 possibilities here, if it's a gas, which all of these are gas, it's a lowercase g in italics that's in a subscript. If it's a liquid, it's a lowercase l in italics as a subscript. Aqueous solution is AQ, and solid is S. But it's pretty self-explanatory, especially once you see it over and over again. Coefficients are the big numbers, like this number 2, that gets put in to balance that equation. It takes 2 molecules of O2 to react with 1 molecule of CH4 to make 1 molecule of carbon dioxide and 2 molecules of water. Okay? And we're going to learn how to balance the equation in this chapter if you didn't already know. All right. And so, once again, this is just the word way of saying what I've been stating on this. Right? So, do not get confused with the subscripts and the coefficients. The subscripts are the lowercase letter, not lowercase, but the smaller numbers that are below the line, whereas the coefficients are the big numbers. And this is a lot like math in that this means, the subscript means that there's 2 hydrogens to 1 oxygen, like what we've been doing for our formula. But whenever you put the big 2, that means there's a total of 4 hydrogens and 2 oxygens there, okay? Because you multiply everything that's within it, just like, you can almost imagine it being like this, 2 times H2O. We just don't put the parentheses around it. Because it takes 2 water molecules to do the reacting. All right? So, let's look at this example here. We're going to balance this equation. This is sodium metal, so it's solid sodium reacting with water, which, by the way, it's very reactive. You don't want to do this. We'll make sodium hydroxide, and it gives off hydrogen gas. But we've got to balance the equation. It may already be balanced, but it may not be. And so, without skipping any steps right now, I'll show you how to do this. Like if you want to, or one way to do it, is you just simply write out Na, H, and O. And I strongly suggest that you put off balancing the oxygens and hydrogens until late. Okay? Usually you don't want to balance them first because sometimes you want to balance the non-oxygens and hydrogens first because sometimes, well this time it's not one of those times, but sometimes that will help out in balancing the overall reaction. And so we have our reactants and we have our products. And I apologize if I ever say substrates and products because in biochemistry we call the reactants substrates. All right, so we have, right now, there's 1 sodium on the reactant side, 1 on the product side. How many hydrogens right now are there on the reactant side? 2, because there's 2 in the water. How many total do we have on the product side? 3. Okay, and how many oxygens do we have on each side? 1. So really, it's the hydrogens that are out of whack. Right? So we have to think of a common multiple, what is that, least common multiple, of hydrogens. So what is the least common multiple of 2 and 3? 6. So that means we have to multiply this by 3 to get 6, and this one by 2. Okay, so what that means is now I'm going to just rewrite the Na, and at this time I'm not going to write the solid part just because I don't have that much room. And it's going to take 3 waters to make NaOH plus H2. Well, by putting the 3 waters there, now we've got 6 here, but we've got a total of 3 oxygens. So now the oxygens are out of whack on the product side. So how can we go about making 3 oxygens on the product side? Where do we put a coefficient and what should that number be? How can we turn, let me put a different color, and make over here 3 oxygens? Put a 3 in front of what? The sodium. Of course, now we've got 3 sodiums. We've got 3, 4, 5 hydrogens, but we need 6. right? Because there's 3 plus 2 is 5. And we've got 3 oxygens.